Sure.
First of all, Prashant is here. Good
Good
evening,
evening,
Prashant.
Prashant.
We were
We
waiting
were
for you.
waiting for you.
Hey, sorry, Nishant. Yeah, I was
It's
a little
okay.
bit
It's
busy.
okay.
Anyway,
Thanks.
Anyway,
anyway,
can you guys see my screen?
Yes.
Okay, great.
Okay, great.
First of all,
First of all,
let's start
let's
off with
start off with
the generic
the
question I
generic question
always
I
ask.
always ask.
Any
Any
questions with
questions with
any
any
questions about
questions
from
about
week
from
9
week 9
assignment?
assignment?
Week 9 assignment. Yeah, nothing there.
Week 9, what was the assignment?
Week 9
Week
was
9 was
this
this
band gap
band gap
references.
references.
No,
Oh, no,
actually,
week 10 is band gap report, right?
week 10 is
Is it?
band
Okay,
gap.
so
Okay,
we
so
should
we should
discuss week
discuss week
10 now,
10 now,
right?
right?
No?
No?
Or week
Or
Yes,
week
9?
yes.
9?
Week 10
Week 10
assignment
assignment
deadline is
deadline
when?
is
This
when?
week,
This
is it?
week, is it?
This week.
This week,
Okay,
this
Okay,
week.
so,
any doubts
any
from
doubts
week
from
9
week 9
assignment then?
assignment?
Week,
No problem.
no, I think. No, week 9, we have solved all right.
Yeah, we already solved it.
Okay,
Okay,
great.
great.
So
So
week
week
10 we'll
10 we'll
discuss in the
discuss in the
next week,
next
I
week, I
suppose.
suppose.
Correct?
Correct?
Yeah.
Okay.
Okay.
Week 9, I have with like,
Because you
Because
have
you
to
have to
send me
send
the
me the
questions
questions
again.
again.
yes. So,
Which one, Vikas?
week 9 means 4 and 5, just means finding the question, like you had the question, no, Prashant, you were saying,
Correct. Yes.
you can just send, you have, okay, I have. So I'll just send Nishant the PDF.
No, I can share the link. Wait, I will do it.
You can share the link. Yeah, he wants the assignment, right?
Chat
Chat
window is
window is
also
also
okay.
okay.
Yeah, I'll share that Google Meet. Yeah, this
Yeah,
one.
Yeah,
got it.
got it.
Great.
Great.
Which
Which
problem,
problem,
Prashant?
Prashant?
Uh, okay, so
About 4 and 5 now.
4 and 5. I mean, five, no, fourth one, not fifth one.
Ha.
Okay.
Okay.
So
So
what is the
what is the
problem?
problem?
The problem was, the GM odd not square will come for, R out will be there for the cascade amplifier, right? And the
Correct.
Correct.
current mirror.
Correct.
Correct.
So in some cases we are taking approximation, right? GM odd not square. In some cases, in this case, we have to take the whole expression, GM odd not square plus 2 odd not.
Hmm.
So why that? I mean, with that
No,
both.
he actually first question about question, how to get the question point for that. So he had the question, actually Prashant asked me question, he like,
One second.
while for getting question, shall we actually consider the R naught? Because lambda we don't consider for getting question AC
Yes.
pairs and band, right?
Nishan. So, okay, I got clarity now. Problem 4, usually when we considering the quiescent point, we will ignore lambda equal to 0 only, right?
Correct,
Correct,
sir.
sir.
We'll assume.
Correct.
Correct.
But in the problem 4, when we try to assume lambda equal to 4, we are getting quite different answer than what the previous year problems are.
Perfect.
Perfect.
No,
No,
I
I
get the
get the
question,
question,
right?
right?
The
The
question
question
is
is
how do
how
you
do you
determine
determine
quotient
quotient
voltage
voltage
at the
at the
output,
output?
correct?
Correct?
Correct.
This
Yes.
is
This
a
is a
trick
trick
question,
question,
okay?
okay?
You
You
have
have
to
to
understand
understand
that
that
this
this
op
op
amp,
amp.
okay,
Okay,
let
let
me
me
just
just
take a
take a
screenshot.
screenshot. I
I
think
think
that is better.
But again, we will end up with the same answer only, no?
You
You
will
will
end
end
up
up
with
with
the
the
same
same
answer,
answer,
but there
but
is
there is
a
a
catch,
catch,
okay, in
okay,
this
in this
question.
question.
Yes,
Yes,
the
the
output
output
quotient
quotient
voltage
voltage
is
is
the
the
VGS
VGS
of
of
the
the
low.
low.
No, just one
Just one
second. I'm
second. I'm
just
just
copying the
copying the
question
question.
here. Yes,
Yes,
great.
great.
Huh.
Huh.
Yeah.
So the
So the
quotient
quotient
output
output
voltage
voltage
here
here
will be
will
the
be the
VGS of
VGS
this
of this
fellow,
fellow,
correct?
correct?
Because the
Because the
currents here
currents
are
here
the
are the
same.
same.
If
If
Yeah.
VG is
Yes.
VD is
0,
0,
the
the
currents here
currents
are
here
the
are the
same.
same.
And
And
if the
if the
lambdas is
lambdas
the
is the
same,
same,
then
then
this
this
potential
potential
has to
has
be
to be
equal to
equal
this
to this
potential,
potential,
correct?
correct?
Yes. Correct.
This
This
is
is
fixed
fixed
by
by
VDS,
VDS,
correct?
correct?
With
With
lambda.
lambda.
Oh, correct. Yes.
If
If
lambda
lambda
was
was
0,
0,
let's say
let's say
ideally,
ideally,
Hmm.
how would
how would
you
you
determine this
determine this
potential?
potential?
Okay, the
Okay, the
question is
question is
can you
can you
determine this
determine this
potential?
potential?
Okay,
No.
let us track that.
Yeah, we can. No, we can. No, we'll take the VGS of the diode connected and then determine it. No?
Yes,
Yes,
sir.
sir.
So the
So the
VGS
VGS
will be
will be
developed
developed
here,
here,
correct?
correct?
There
There
is
is
50
50
micro
micro
here,
here,
50
50
micro
micro
here.
here.
Fair
Fair
enough.
enough.
Yes.
Now,
Now,
how did you?
okay,
Let's say lambda is equal to
100 micron. Nishan, 100 micron.
Okay,
Okay,
fine.
fine.
Some
Some
current.
current.
Prashant.
100 micro, 100
micro.
micro.
Fair
Fair
enough.
enough.
Yes.
Now,
Now,
if
if
lambda
lambda
n
n
is
is
0.1,
0.1,
how did you
determine
determine this
this
potential?
potential?
I will make. Yeah, I'll remove that current mirror and connect directly to the resistor R out, whatever I get.
Okay,
Okay,
no,
no,
no.
no.
In
In
quasi
quasi
end,
end,
you
you
should do
should do
I1
I1
equal to
equal to
I2,
I2,
correct?
correct?
This
This
current is
current is
equal to
equal to
this
this
current.
current.
Yes, yes.
Then
Then
1
1
plus
plus
lambda
lambda
VDS1 will
VDS1
be
will be
equal to
equal to
1
1
plus
plus
lambda
lambda
VDS2,
VDS2,
correct?
correct?
Yes.
And
And
hence you
hence
will
you will
get
get
VDS1
VDS1
equal to
equal to
VDS2.
VDS2.
Oh,
Oh,
okay.
okay.
Let's say
Let's say
this is
this is
M1 and
M1
this
and
is
this is
M2.
M2.
Okay,
Okay,
I
I
think I'm
think I'm
confusing you.
confusing you.
Let's
Let's
say
say
this is
this is
M1.
M1.
Okay,
Okay,
and this
and
is
this is
M2.
M2.
Uh-huh. Yeah, okay.
Fair
Fair
enough.
enough?
Yes.
If
If
VD is
VD is
0,
0,
I1
I1
has to
has
be
to be
equal to
equal to
I2. Do
I2. Do
you
you
agree?
agree?
VD is 0.
If
If
VD
VD
is
is
0,
0,
you
you
connect
connect
VCM
VCM
on
on
both
both
nodes.
nodes.
Yes, yes. I1 is equal to I2, correct.
So
So
if
if
what
what
is
is
I1?
I1?
I1 is
I1 is
half
half
nu
nu
and
and
C
C
ox
ox
W by
W by
L.
L.
VGS
VGS
minus
minus
VTH
VTH
whole
whole
square
square
into
into
1
1
plus
plus
lambda
lambda
VDS1,
VDS1.
correct?
Correct?
Yes.
This
This
becomes
becomes
equal
equal
to
to
half
half
nu
nu
and
and
C
C
ox
ox
W
W
by
by
L,
L.
VGS
VGS
minus
minus
VTH
VTH
whole
whole
square
square
into
into
1
1
plus
plus
lambda
lambda
VDS2.
VDS2.
Fair
Fair
enough?
enough?
Yeah.
This,
This
this,
this
this,
this
this,
this
this,
this
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 will
will
get
get
cancelled.
cancelled.
Fair
Fair
enough?
enough?
Yes, yes, yes.
So
So
VDS1
VDS1
becomes
becomes
equal to
equal to
VDS2.
VDS2.
Hmm.
But
But
M1
M1
VGS1 is
VGS1 is
equal to
equal to
VGS1.
VGS1.
Hmm.
And
And
hence
hence
VDS2
VDS2
becomes
becomes
VGS1.
VGS1.
Correct?
Correct?
Yes.
This is
This
how
is
you
how you
determine.
determine.
So
Yes.
this is with the case with RO
With
with finite
lambda.
finite
With
finite
finite.
ROS.
Correct?
Yes.
Now
Now
let's say
let's say
lambda
lambda
equal to
equal to
0.
0.
Ideal
Ideal
case.
case.
How
How
would
would
you
you
determine
determine
this
this
potential?
potential?
Same I.
So
I1 is
that
still equal to
Equal to
I2.
I2.
I1 still equal to I2. And left side it will be yeah only overdrive will be there. So this can be anything, right? Yeah,
Exactly.
Exactly.
You
You
got it
got it
because
because
this
this
potential
potential
can
can
be
be
anything.
anything.
anything high
It can be anything.
low impedance.
So,
But
but
High
one
impedance.
one catch
catch
is
is
that you
that
will
you will
use
use
this
this
op
op
amp
amp
in
in
a
a
feedback
feedback
circuit
circuit
always.
always.
So that will determine that feedback.
Exactly. You
You
get
get
it,
it,
right?
right?
This
This
feedback
feedback
will
will
determine this
determine this
potential.
potential.
Like,
Like,
for
for
example,
example,
let us
let
say
us
I
say I
put
put
this
this
op
op
amp
amp
inside
inside
this
this
feedback
feedback
loop.
loop.
Yes.
Okay.
Same only. Yeah.
And
And
let's
let's
connect
connect
this
this
to
to
VCM
VCM
because I
because I
want
want
0
zero
input
input
to
to
determine.
determine.
Fair
Fair
enough?
enough?
Yes.
So
So,
what
what
does
does
that
that
mean?
mean?
To the
To the
output
output
terminal
terminal
and
and
the
the
negative,
negative,
which is
which
this
is
is the
this is the
negative
negative
terminal,
terminal,
right?
right?
This is
This is
negative, this
negative,
is
this is
positive.
positive.
Yes. Yes.
Correct, no,
Correct, no,
Vikas?
Vikas?
Yes.
So
So,
what did
what
I
did I
do? I
do? I
take the
take the
output
output
terminal,
terminal,
connect
connect
resistor,
resistor,
resistor to
resistor to
ground,
ground,
or I
or
mean
I
to
mean to
VCM.
VCM.
VCM. Then yeah.
So
So,
this
this
potential
potential
becomes
becomes
VCM.
VCM.
Yes.
The
The
feedback
feedback
network
network
sets
sets
this
this
potential.
potential.
Correct.
You
You
see it,
see it,
right?
right?
Got it.
Fair
Fair
enough,
enough,
Vikas.
Vikas.
I
I
mean,
mean,
fair
fair
enough,
enough,
Prashant.
Prashant.
Yes. Yes.
Mm-hmm.
The
The
feedback
feedback
network
network
will
will
determine the
determine the
quasi
quasi
potential
potential
of
of
the
the
op
op
amp.
amp.
Okay. So without R naught, we were not able to find in the open loop like what is
Yes.
V out. It will be
Yes.
impossible.
Exactly,
Exactly,
sir.
sir.
Yes.
Got
Fair
it.
Fair
enough.
enough?
Yeah. Yeah. Got it.
That
That
is why
is why
lambda
lambda
is
is
given in
given
the
in the
question.
question.
Hmm.
But
But
this is
this is
a
a
trick
trick
question. I
question.
mean, I
I
would.
would.
Oh, my
Oh, my
video is
video is
not
not
on.
on.
I
I
have
have
been
been
persecuted for this
persecuted for
mistake
this
before.
mistake before.
So
And this presentation actually can you make it big, getting it small left side?
Mm,
So last time you made no actually, and then we only can need to see right full
you
screen.
have
you
to
have
make
to
it,
make it,
You,
Prashant.
Prashant.
you
So
have
So
to
right
right
click,
click,
full
full
screen.
Full
screen.
screen. Okay. Okay.
Okay.
Change layout spotlight.
Change layout.
Change layout, yes.
Then
Then
okay,
spotlight.
spotlight. Okay.
Great.
Thank
Great.
you. Yes,
Works.
yes. Yeah.
Okay.
Now,
Now,
did you
did you
guys
guys
understand
understand
this?
this?
This
This
is
is
very
very
important.
important.
This
This
the
the
output
Yes.
output
potential
potential
of
of
the
the
op
op
amp
amp
is
is
always
always
fixed
fixed
by
by
the
the
feedback
feedback
circuit,
circuit,
Okay.
not by the
not by
op
the
amp
op amp
itself.
itself.
Correct.
Fair
Mm-hmm.
Fair
enough.
enough?
Got it.
Okay,
Okay,
great.
great.
Now, any
Now,
other
any other
questions from
questions
week
from
five?
week 5?
I mean,
I
week
mean, week
nine.
9.
Sorry, week
Sorry.
nine.
Week 9, the fifth question, if we go, the cascade CM will be, the R out of that is GM odd naught square plus 2 odd naught, right?
1 minute, sir. Where is it? Because,
You
you
sent it
sent
me.
it me.
Yeah, I sent a
Okay.
link. No?
We
Fifth
fifth
question.
question.
What should
What
I
should I
see?
see?
Fifth question, basically they asked for the gain,
Ha.
gain of it, right?
Ha.
So for that we need to get 2 GM R out. R out is basically GM odd naught square plus 2 odd naught, right?
Looking
Looking
down is
down is
GM R
GM R
naught
naught
square.
square.
Plus 2 odd
Looking up.
naught,
Looking
right?
up.
Plus.
Plus,
Okay,
okay,
fine. 2
fine.
plus
2
2
plus
R
2 R
naught,
naught,
whatever.
whatever.
Looking up.
Looking up.
Looking up, it will be GM only, right? I mean,
Oi.
Oi,
it will be 1 by
Oi. Lambda
lambda
P
p is
0.
0.
correct.
So
So
what does
what
that
does that
mean?
mean?
Lambda p
Infinite.
Looking up
Looking
is
up is
infinite now.
infinite now.
infinite. Lambda
Correct?
Correct?
p correct. Lambda p 0, correct. Infinite. It's 1 by 0. It's
Hmm.
So
So
what is
what
the
is the
output
output
impedance?
impedance?
yeah, no. When we do that approximation, we R out is equal to GM R naught square. We are getting different R out, but gain is varying a lot actually by 100 times.
No, I didn't get you. That determines the incremental output voltage.
Hmm.
What is the incremental output voltage? That's what is being asked.
No,
Now, what is the Okay, let me copy that.
No. What he means to say, I think the around, if you just take GM RO square
Hmm.
and actually GM RO square plus 2RO. So
Is there
Is
a
there a
huge
huge
if
difference?
you ignore the 2RO, then the gain difference is too much is getting around.
Yeah. The gain difference is what we are seeing too much actually.
I
I
don't
don't
expect that,
expect that,
Prashant.
Prashant.
No, Nishant, here the gain actually expected is 1700. Okay.
Huh.
But when we do approximation for R out, taking only the GM odd naught square, the gain we are getting is 1600.
Okay.
Okay.
I mean, there is a difference of 100.
That's
It's
okay,
okay,
yaar.
yaar.
1600,
1600,
1700 is
1700 is
not a
not a
big,
big,
I mean,
big
we
delta,
cannot
really.
reduce the marks, right?
It's
It's
okay,
okay,
yaar. Who
yaar. Who
cares
cares
about
about
marks?
marks?
The
The
thing is,
thing
you
is,
should
you should
learn.
learn.
That's all
That's
you
all you
should
should
care
care
about.
about.
Okay.
Okay.
Don't
Don't worry.
don't care
Care
about
about
anything
Yeah,
anything
else.
else.
I mean, usually we take approximation, but I saw this was a huge gain change. Then,
No,
No,
yeah,
1600 to
1600 to
1700
1700
only.
only,
No,
no.
yes.
this is
This is
not a
not a
huge
huge
change.
change.
Okay.
Sir,
You should
you
look
should
at
look at
ratio,
ratio,
yaar.
yaar.
When you're
When you're
talking
talking
about error,
about
now
error,
you
now
don't
you
do
don't do
subtraction.
subtraction.
Hmm.
You should
You
do
should do
subtraction by
subtraction by
original
original
value
value.
Correct.
into
Into
100. This
100.
is
This
your
is your
error,
error.
not
Not
this.
this.
Okay.
Fair
Fair
enough.
enough?
Yes.
I
I
mean,
mean,
1e9
1e9
minus
minus 1
1e9
1e9
plus
plus
100
100
also
also
has an
has an
error of
error of
100.
100.
Yes.
But you
But you
divide it
divide
into
it into
1e9 and
1e9 and
multiply by
multiply by
100,
100,
na,
na,
the
the
error will
error
be
will
very
be very
small.
small.
Right.
So you should
So you should
always
always
talk
talk
about
about
relative
relative
error
error
in
in
percentages.
percentages.
Okay.
Okay,
Okay,
fair
fair
enough.
enough?
Yes. I mean, that's all from me. From week 9, Asa, I mean, videos, right? Sir has jumped many topics like poles and zeros. He never explained what is the basics of that and how it is. What is that, right?
Hmm.
He directly went into solving all that CGC. I mean, all the amplifier transfer functions.
Okay.
Okay.
I mean, that was quite confusing actually.
Okay, let
Okay,
me
let
try
me
to
try
help
to
you
help
today.
you today.
Okay,
Okay,
you try
you try
to
to
answer
answer
the
the
questions that
questions
I
that I
ask you.
ask
Fair
you.
enough.
Fair enough?
Okay.
I
Yeah.
think
I
it will
think it'll
brush
brush
up
up
your
your
basics
basics
as
as well.
Sure.
well. Okay.
Okay,
Now
now
let
let
us
us
start
start
with
with
a
a
very
very
primitive
primitive
design.
design.
Okay.
Okay,
Let us
let
say
us say
someone is
someone is
asking you
asking
to
you to
design a
design a
buffer.
buffer.
Okay.
The arena opens up to everyone. So
So
what
what
does
does
the
the
system
system
engineer
engineer
give
give
you? He
you?
gives
He gives
you
you
what is
what is
the
the
drive?
drive.
What is
What
the
is the
resistance that you
resistance that
have
you
to
have to
drive,
drive,
and what
and
is the
what is the
capacitance you have
capacitance
to
you have
drive.
to drive.
Correct, right?
Correct, right?
Yes.
Let's
Let's
say
say
someone is
someone is
asked,
asked,
the
the
system
system
engineer will
engineer
come
will
and
come
tell
and
you,
tell you,
boss, I
boss,
need
I
a
need a
buffer.
buffer.
There is an
There is an
input,
input,
right?
right?
And
And
I
I
need your
need your
buffer,
buffer
or
or
what is
what
that?
is that?
Gain.
Gain.
Okay,
Okay,
let's call
let's
it
call it
in
in
a
a
gain
gain
block.
block.
Unity again.
Not
Not
unity gain.
unity
Let's
gain. Let's
call it
call it
gain
gain
block.
block.
Fair
Fair
enough.
enough.
The
The
Driver
gain
gain
block.
block
block
has
has
to
to
drive.
drive.
Let's say the
Let's say the
gain I
gain I
want is
want is
10.
10.
Okay,
Okay,
has to
has to
drive a
drive a
10
10
nanofarad
nanofarad
cap
cap
and
and
a
a
1
1
kilo ohm
kilo ohm
resistance.
resistance.
Okay,
Okay,
this is
this is
what
Okay.
what
system
system
engineer will
engineer
give
will
you.
give you.
Correct.
Correct.
Hmm.
Now,
Now,
so
so
what is your
what is your
first
first
thought that
thought
comes
that
to your
comes to your
mind? You
mind?
would
You would
put
put
this,
this,
or you
or
would
you would
put
put
this.
this.
Connect this
Connect
to
this to
ground. You
ground.
would
You would
connect this
connect this
to
to
input.
input.
You would
You would
connect
connect
R and
R and
9R.
9R.
Correct.
Correct.
Okay.
You would
You
get
would
a
get
gain
a
of
gain of
10.
10.
Hmm.
Now,
Now,
the
the
first
first
question
question
is,
is,
how do you
how do you
decide this
decide
R
this
in?
R in?
Correct.
Correct.
Yes.
So how
So
do we
how do we
decide?
decide?
I'm
I'm
designing with
designing with
you. I
you.
am
I am
also a
also a
fresh
fresh
designer.
designer.
Okay. Can you come again? I
See,
quite a.
See,
okay,
okay,
you
you
have to
have to
design a
design a
gain
block
block
gain
of
block of
10.
10.
Okay.
Correct.
Correct.
This is
This
the
Yeah.
is the
first
first
thing
thing
that
that
comes to
comes
your
to your
mind.
mind.
Correct,
Correct,
right? At
right?
least
At
it
least it
comes to
comes to
Yes.
my
my
mind.
mind.
Yes. Yes.
Right?
Right?
The
The
system
system
engineer
engineer
does,
does,
boss, you
boss,
have
you have
to
to
drive a
drive a
10
10
nanofarad
nanofarad
cap and
cap
1
and 1
kilo ohm
kilo ohm
load.
load.
Correct?
Correct?
Yes.
Now,
Now,
first
first
thing
thing
first
first
is you
is you
have to
have to
determine
determine
what
what
Rn
Rn
is.
is.
Yeah, we know the gain equation minus R2 by R1.
I
I
1 plus
1 plus
R2 by
R2 by
R1.
R1.
1
This
plus.
is
Oh, okay. Yeah,
this
this
is
is a
point.
positive. Correct. Correct.
So that
That
is
is
10.
10.
The
The
ratio,
ratio,
na,
na,
R2 by
R2 by
R1 is a
R1 is a
ratio.
ratio.
Yes.
I've
I've
chosen that
chosen
as
that as
9,
9.
but I
But I
want to
want to
find out
find
if
out
this
if
should
this
be
should be
1
1
ohm or
ohm or
1
1
kilo
kilo
ohm
ohm
or
or
10
10
kilo ohm
kilo
or
ohm
1
or
mega
1 mega
ohm. How
ohm.
do I
How do I
decide?
decide?
That will come from the
Based on the
output.
frequency or the bandwidth which is supported by the
Okay,
load.
Okay, 1 minute, 1
1
minute, 1
minute.
minute.
So
So,
first
first
question is
question is
bandwidth.
bandwidth.
Next,
Next,
A unit. I mean, yeah, bandwidth gain we already know.
gain we
gain we
know.
Uh,
know.
yeah, and maybe the phase shift. Phase shift is also one more thing.
Phase
Phase
shift
shift
from
from
input to
input to
output.
output.
I mean, phase margin. I mean to say.
No,
No,
does
but does
phase
phase
margin
margin
depend on
depend
the
on the
choice of
choice of
this
this
resistor?
resistor?
Uh, not. Yeah, maybe right.
No.
No.
At
At
least
least
no
no
for
for
till
till
first
first
order.
order.
Okay.
The DC gain,
Hey,
Hey,
DC
DC
gain is
gain is
10
10
man.
man.
And
10
10.
man. We already, we already knew it.
then stability, sir,
Sorry?
Sorry?
stability.
I
Stability.
didn't
I
get
didn't
you.
get you.
What?
What?
Stability.
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 Okay.
Okay.
Does
Does
the
the
actual
actual
the
the
pure
pure
value of
value of
Rn
Rn
determine
determine
stability?
stability?
No, no.
Let's say I
Let's say
use
use
1
1
ohm.
ohm.
Okay, let's
Okay,
say the
let's say
op
the
amp
op
is
amp is
ideal, yeah.
ideal. Yeah,
The op
the
amp
op
is
amp is
ideal. There
ideal.
is
There
no
is no
stability
stability
problem.
problem.
Now, how
Now,
do I
how do I
determine
determine
Rn?
Rn?
Yeah, that will come from the route sleeve rate actually, because that will decide the current. No, RN will decide the current, which will other which will
This
This
current, no,
current,
no,
no,
I
no,
didn't
I
get
didn't
you,
get you,
Vikas. Come
Vikas. Come
again?
again?
yeah, since value of RE will decide the current going from output to input side. So that will basically determine the output sleeve, meaning output rise time. So what out,
Vikas, the
Because
op
the
amp
op
is
amp is
ideal.
ideal.
yeah, op-amp is ideal. Okay,
Huh.
op-amp is ideal, you're saying.
Huh.
But see, even though the op-amp is ideal, how the output sleeve will happen? That sleeve will happen with V in by R in only current only, right?
Oh
Oh
no,
Ideal.
no,
because
because
the
Ideal.
the
op
op
amp is
amp is
ideal.
ideal.
It'll
It
give
will
you
give you
whatever
whatever
current you
current you
want.
want.
Yeah, take
Okay,
unit step response only.
okay.
The
Assume
power
unit
dissipation,
is a response.
The
The
op amp
op
is
amp is
ideal,
ideal,
yaar.
yaar.
Ideal,
Okay.
man.
Op-amp ideal. Then how do we decide R in values?
Huh.
Okay.
Yes.
Yes.
How to decide R in value for actually, if R in Yeah, that will actually change our output pool, right?
Yeah, the op-amp is ideal.
Now, open ideal, yeah, and then anything we can put.
Okay,
Okay,
let's
let's
say I
say I
put
put
1
1
mega
mega
ohm.
ohm.
Hmm.
What
What
happens?
happens?
Okay, do
Okay,
you
do
think
you
it
think
will
it will
work?
work?
Yeah, it
Have you
will.
Have you
heard
heard
about
about
thermal
thermal
noise?
noise?
Yes,
Yes.
sir.
Right?
Right?
Thermal
Thermal
noise
noise increases with increase in
Temperature.
Resistance.
resistance.
Temperature,
Temperature,
yes,
yes,
but
but
4
4
kT.
kT.
Okay,
Okay,
okay.
okay. I think I should have told this to you. Is
If we
if you
choose
choose
high
high
and high
and high
resistance,
resistance,
the
the
noise
noise
here,
here,
thermal
thermal
noise
noise
here,
here,
will
will
keep on
keep on
increasing.
increasing.
Correct?
Correct?
Hmm.
Fair
Fair
enough?
enough?
Right. Hmm.
So someone should
Someone
tell
should tell
you the
you the
thermal noise
thermal noise
specification.
specification.
I
I
need
need
so much
so much
SNR
SNR
here.
here.
Right.
Let's say
Let's
the
say the
SNR
SNR
needed here
needed
is
here is
80
80
dB.
dB.
You will
You will
choose
choose
this
this
resistance such
resistance such
that you will
that you
get
will get
80
80
dB
dB
SNR.
SNR.
You're
You're
understanding?
understanding?
Correct.
Okay.
Above
So
80 watt, yes.
there is a
There is a
way to
way to
determine
determine
at
at
the
the
input
input
resistance
resistance
given an
given an
output
output
SNR.
SNR.
Okay.
Okay?
Let's say
Let's
I
say I
have done
have
that
done that
math.
math.
And I'm
And I'm
telling you
telling you
that this
that this
resistance
resistance
for
for
thermal
thermal
noise
noise
specification has
specification
to
has
be
to be
10K.
10K.
Below 10K.
No,
No,
below
below
10K,
10K,
but
but
you should
you should
choose the
choose the
highest
highest
value that
value
is
that is
okay
okay
for you.
for you.
Okay. Okay.
Fair enough?
Fair
Why?
enough? Why?
If I
If
choose
I choose
10 ohm,
10
what
ohm,
will
what will
happen?
happen?
10 ohm
10
and
ohm and
90
90
ohm?
ohm?
Huge current will flow.
Exactly.
Exactly.
This
This
current is
current is
what
what
we in
we
by
mean by
10 ohm,
10 ohm,
correct?
correct?
Yes.
And that
And that
current has
current
to be
has to be
supplied by the
supplied by
op
the op
amp.
amp.
So
Yes.
the
So the
current
current
out will
out
be
will be
huge.
huge.
You are
You are
getting it,
getting
right?
it, right?
Hmm.
So you
So
should
you should
use
use
the
the
maximum
maximum
resistance
resistance
possible
possible
for the
for the
thermal noise
thermal noise
specification.
specification.
Okay.
Fair
Fair
enough?
enough?
Did you
Did you
guys
guys
get it?
get it?
Yes.
Okay.
Yes.
Okay.
So
So
thermal
thermal
noise
noise
determines
determines
The maximum resistance of
the
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 maximum
maximum
resistance.
resistance.
Okay.
Okay?
So can
So
we
Okay.
can
move
we
on?
move
We have
on? We have
decided R
decided
in
R
ka
in ka
value.
value.
Fair enough?
Fair enough?
Now the
Now the
question is
question is
how do
how
we
to
Yes.
decide the
decide the
op
op
amp?
amp.
Okay, the
Okay, the
question is
question is
what all
what all
questions will
questions
you
will you
ask?
ask?
This is a
This is a
question to the
question to the
system
system
engineer,
engineer,
correct?
correct?
What all
What all
questions will you
questions will
ask
you
to the
ask to the
system
system
engineer?
engineer?
Okay. So what is the offset?
Okay,
Okay, tertiary question, primary
question.
question.
Primary question is how fast you want your output to change.
In
In
other
other
words,
words,
what is
what
the
is the
bandwidth?
bandwidth?
Bandwidth is the bandwidth.
What
Yes.
is
What
the
is the
bandwidth
bandwidth
of
of
operation?
operation?
Yes.
Yes.
Next.
Next.
And
Bandwidth of operation. Then even this will also come.
PSRR.
Output sleeve also will come. So output sleeve meaning what is the rise time he wants to.
Okay,
Okay,
output
output
slew.
slew.
Fine.
Fine.
Next.
Next.
PSRR.
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 Okay.
Open
Secondary.
Secondary question.
Secondary question like offset only.
This
This
is
is
primary
primary
question.
question.
Okay,
Okay,
let's
let's
make a
make a
list.
list.
Primary.
Secondary.
PSRR
PSRR
and
and
then
then
output
output
offset.
offset.
Then
Then
CMRR.
Area.
CMRR,
CMRR, a
single-ended
single-ended
circuit.
circuit.
Okay.
Area.
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 Okay.
Okay.
Power.
Thank you.
Power is that.
Dissipation.
Okay.
Okay.
Great.
Great.
These are
These
the
are the
primary
primary
questions that
questions
you
that
will
you
ask.
will ask.
Right?
Right?
And there
And
is
there
one
is
more
one more
primary
primary
question
question
that
that
you
you
guys
guys
are
are
not
not
asking,
asking.
which
Which
is
is
Supply.
no.
no. Okay. Supply voltage is
fixed for
fixed
a
for a
given
given
technology, so
technology.
that
So
is a
that is a
generic
generic
question. That
question.
is
That is
zeroth
zeroth
question. We have
question. We have
already
already
asked
asked
that.
that.
One more
One more
question.
question.
Come
Come
on.
on.
Think.
Single limit.
Sorry?
Sorry?
Swing
Swing
limits.
limits.
Okay,
Okay,
great.
great.
One
One
more.
more.
This
This
comes
comes
somewhere in
somewhere in
between.
between.
Swing limit here anyway doesn't matter, right?
Yeah, it
It
comes in
comes in
between
between
because it's
because
not
it's not
something that you
something
can
that you can
completely
completely
neglect.
neglect.
Okay.
At least when you're starting to design.
Hmm.
One more, come on.
Power distribution comes in
How
bias.
no. How accurate should the gain be?
Hmm.
How
Hmm.
accurate? See, you
No,
needed
and
10,
that
right?
will come on output accuracy. That will come in the output accuracy, right?
Because the question is the system engineer needed gain of 10, correct?
Yeah, that will correct. Get out 10, but that will come with the output accuracy, how much accuracy he wants, right?
Yeah, that
I
comes with
mean,
the offset also, no? I mean, it depends on offset, I agree.
oh no. Okay, here the
See,
question.
gain
The
value
question
is
is, can you handle 9.9 to 10.1 or 9.99 to 10.01? The gain.
Variation, you mean to say?
The gain closed loop gain variation.
Okay,
How
across
much you
PVT.
can handle?
Hmm.
You're understanding, right?
Mm-hmm.
He needed 10, but I can't give 10, correct? I can't exactly give 10. This is analog, not digital.
Got it.
Yeah, that is true. Again, but that if we see output, see anyway, V will be given and the output will be range will be there. So that this can be covered in output accuracy, right? That's what it is.
I don't get you because what do
Output
you mean?
accuracy meaning output DC accuracy, right? Let's say V in okay, V in range also we need to ask, right?
No. The system engineer is intelligent. Nah. If he says I need a gain of 10, he will ensure that he puts an input which doesn't kill the op amp, correct?
Yeah, that is there. But we are the designer, so we need to give the V in range also, right? We need to ask actually.
No, because the supply is fixed, correct?
Hmm.
If the supply is fixed, let's say 1 volt is your supply,
Hmm.
and you need a gain of 10.
Correct.
This maximum it can only swing 0 to 1 volt, correct?
Correct.
Means plus or minus 500 millivolt.
Hmm.
If he asks for a gain of 10 and gives a 1 volt signal here, he is an idiot. It's not on you.
True, true. This point input should be below 100 millivolt only. Yeah.
Below 50 millivolt only it should be.
Hmm.
You're understanding now?
That is clear. Then gain you are saying correct and output. Okay, I'm saying the other way. Again, even we have that is important. Yes. Otherwise, here, if this is gain is 10. Otherwise, if this is B2 even buffer, that we can get it in the output accuracy, right?
No, I don't understand what you mean by output accuracy, Vikas.
Output accuracy meaning, let's say you want output as 1 volt. In this case, the gain buffer.
Oh, okay. Understood. So you're telling the gain variation in output terms.
Right.
Fair enough. But I can model it like this, right? The gain has to be 10.
Again, since here gain is 10, so we can, we can actually give the
You should
specification.
ask the system engineer, boss, what is your accepted values? I can't definitely give you 10.
Yes,
like
yes.
standard deviation, 3 sigma, 2 sigma.
So that's exactly. So mismatch is another problem, but the basic problem is, boss, can you accept anything around the 9.9 to 10.1 or 9.99 to 10.01? Oh, okay. So what does this give us? Okay, why is this piece of information very important? I put it under primary.
Yes, yes. Because that's what it is supposed to do, main function.
So what does that give me when during op-amp design with us? How does this help me? How does this value help me?
There is a quiescent value.
Sorry?
It varies in the quiescent value of the op-amp.
No,
No,
no. This will actually miss. We need to the mismatch and all. We have to minimize to get this right.
no,
Mismatch. Huh?
because there is a primary problem. The open loop gain of the op-amp changes with
Change in sub.
Correct.
temperature.
Temperature now. Yes.
Across PVT, the open loop gain varies, correct?
Correct. So this will
Let's say by
says
20%.
this will set a minimum limit the open loop gain variations.
Thank you. You guys get it right?
Yes.
I mean, let's say, okay, I will ask you a question. Let's say the accepted limit is 5%, not 5%. Let's say 2%.
2%.
Okay, what does that mean? The gain can be, let's say 1%. It's easy on the math. Yeah, I want 10. It should be between 10.01 to 9.99.
Correct.
Let's say the open loop gain of the op-amp changes by 20% across PVT.
Yes.
What should be A naught? Did you guys get the question?
Yes, yes, yes. Got it.
Yes.
If the
If the
op-amp
op-amp
gain
gain
varies from
varies
zero
from
point
zero
0.8
point
A
0.8 A
naught
naught
to
to
1.2 A
1.2 A
naught,
naught,
the
the
output
output
should
should
vary
vary
between
between
1%
1%
to, I
to,
mean, plus or
plus or
minus
minus
1%.
1%.
Yes.
Hmm.
So we need to take that minimum with zero point 0.8 A naught. The A naught should be such that with zero point 0.8 A naught we should satisfy our condition.
Yes, sir.
Yes, sir.
Correct.
So, how
So
do
how do
we
we
solve it,
solve
sir?
it, sir?
Yeah, it
What
is
is
What is
very
output?
easy to compare.
ADC by
ADC by
1
1
plus
1 plus
ADC
plus
into
ADC into
86 to
10.
this factor.
Fair
fair
enough?
enough?
Does
Does
everyone
everyone
agree?
agree?
ADC is the
ADC is the
open
open
loop
loop
gain of
gain
the
of the
op-amp
op-amp
Yeah.
at a
a
given
given
at a
Yes.
at a
given
given
temperature,
temperature,
whatever
whatever,
it is, correct?
correct?
Hmm.
So
Yes.
So
A
A
naught by
naught by
1
1
plus A
plus A
naught,
naught.
I
No,
mean,
this is actually generally loop gain by 1 plus loop gain comes, no?
that is
That
it.
is a.
Oh, yeah,
Oh, yeah,
sorry.
sorry.
Just one
Just one
second,
second.
please. Just
Just
one
one
second.
second. ಹೋಗು 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 ಅಯ್ಯೋ okay. Okay, sorry for that, guys.
Anyway,
Anyway,
where
where
was
was
I?
I? So
So loop,
loop,
what is
what
loop
is loop
gain?
gain?
ADC
ADC
into
into
Loop gain is ADC into here in this case the 10 will come, is it?
no,
no,
no.
no.
What is the
What is the
beta?
beta?
Beta here is output to this one, right? 9,
Answer
9.
faster
Beta
by
is 9, right?
Oi,
Beta is 9.
oi,
Oi,
think
think
1
1
9
9
okay. 10, 10.
Bit
10.
10.
Hey,
Hey,
what is
what is
beta,
beta,
yaar?
yaar?
1
1 by 10, sir. 1 by 10.
Thank
Thank
you.
you.
by 10.
You
You
see it,
see it,
right?
right?
1
1
by
1
by
by
1
1
1
plus
plus
1 by
Yes,
1
9.
yes,
by
It is
9.
9.
resistive
9
generator.
divided.
So A
Correct,
naught
correct.
ADC by
ADC by
10
10
by
by
ADC by
ADC by
10,
10.
ten,
correct?
correct?
Correct.
Into,
Into,
Barabar.
so
so
loop
loop
gain by
gain by
1
1
plus
plus
loop
loop
gain
gain
into
into
1 by
1 by
beta
beta
into
into
loop
loop
gain into
gain
1
into 1
plus
plus
loop gain
loop
is
gain is
your
your
V
V
out,
out,
correct?
correct?
But this
It
is
is closer to brain.
Win also will come into.
V out
V
by
out by
V
V
in
in
is
Ah,
1 by
1 by
beta
beta
right.
into
into
loop
loop
gain by 1
gain by
plus
1
loop
plus
gain.
loop gain.
Correct.
So this
So
is
this is
10,
10,
correct?
correct?
1 by beta is 10. Okay.
Fair
Fair
enough?
enough?
Correct.
So
So
where
where
does this
does this
become
become
minimum
minimum
when
when
ADC
ADC
is
is
1.8 or
1.8 or
1.2?
1.2?
Oh,
Oh, did
okay.
okay.
If
If
Point.
point 8,
point 0.8,
correct?
correct?
This
This
becomes
becomes
9.99
9.99
Barabar.
by
by
10
10
is
is
equal to
equal
zero
to
point 0.8 A
0.8 A
naught by
naught
10 by
10 by
1
1
plus
plus
zero point 0.8 A
0.8 A
naught by
naught by
10.
10.
Fair
Fair
enough?
enough?
So what
So
is
what
A
is A
naught
naught
from
from
this?
this? I
Guys,
mean,
are you
guys, are you
understanding? This is
understanding? This
very
is very
Yes,
important
yes,
step,
important
yes.
bro.
step, bro.
Yes, yes.
Prashant, what
Prashant, what
about you?
about you?
Yeah, yes. Yeah.
Dhananjaya?
Dhananjaya?
Yes, sir. Yes, sir. Yes, sir.
Hatto,
Hatto,
what is
what
it?
is it?
Standing. Well, it is
Sir,
coming as
15.6.
Sorry?
Sorry?
15.
No, I
No,
didn't
I
get
didn't
you.
get you.
What?
What?
Hey,
no,
Hey,
no,
no.
no.
no,
It is
It can't be.
12,000, 12,480, 487.
let's say 10,000 approximately.
Yes, 12,000 is showing now.
Okay. Now let us say this was 1%. I mean 10% variation. Our limit was not, I don't want that accurate gain. 10%
Correct.
variation is also okay. Now
Yes.
what does this A naught become?
With 10% of 10 volt, it is what, 9 volt, right?
9.9.
No, 9 volt, right? Only.
Oh, sorry. Okay.
It's 1%. Actually, here in this case, we consider 0.01%, actually, very small.
Oh, is it? Okay. Yeah, sorry, man. Yeah. I think point zero. Okay, let's make a table. Okay. Point
Yes.
zero 0.01% it is 10,000.
Yes.
0.1%. I mean, I think this is 0.1%.
0.1%, yes.
1%, 10%. You can get.
1%, yes, we can value it, yeah. So with 1%, it is what, 9.9, right? 9.9.
Prashant, you are understanding what is going on, right? We are trying to find out what is the A naught for percentage variation.
Yes.
Satisfy. Did you understand this math?
Yeah, I understood that. Yes.
Fast. I
It
have a
is
lot of
showing
stuff to tell you.
0.1% something we are missing. How come it is showing 123? Something I missed it.
No, it can be, na.
123 I'm getting.
Can someone else verify? Are you guys verifying? Mm, yeah, 125 should be correct. Yeah, 125. Let's call it 100. No, let's say 10% was okay.
10%, then
Hey, yeah, I'm getting 100. I'm getting 100 here and 1,000 here.
right, right, there should be 1,000. That's what I'm.
Fair enough.
Right. This
Okay.
correct.
So this is easiest to do, right?
Correct.
Let's start from here. Let's try to design op amp where 10% variation is allowed.
Okay.
So the gain has to, let's say the system engineer was like, yeah, give me between 9 and 11, I don't care. Okay. Then you would choose this, right?
Correct.
So the open loop gain of the op amp has to be 100.
100.
Great. No.
Yes.
Let's say a single stage gain is enough for this.
Correct.
How would you model a single stage op amp?
5 pack.
Okay. Let's say in small signal.
Small signal. Okay. GMR out.
See in, correct? VP VN. This will be GM into VP minus VN RO, which RO let's say is GM RO. I know let's say is 100. Okay, for this particular technology, let's say 200. Let's play. Right? So how much would be this RO? Guys, do you guys agree with this model of the op-amp?
Yes, yes.
Right?
Yes.
Can you guys tell me? Okay, so what is unknown here?
GM.
Scene is also a function of GM. Okay. Let's say for every 1 millisiemens GM I need, 1 minute. Okay, I think I should explain this. Right? Let's say I need some GM from the MOSFET, from this MOSFET. Right?
Yes.
Do you guys agree that bigger this MOSFET size, bigger is the input cap?
Yes.
So the scene is a function of the GM that you need, correct?
Correct.
On a simplistic level, on a very simplistic level. Fair enough?
Yes.
So this let's say for every 1 millisiemens GM I need, 1 millisiemens I get some 10 picofarad ka input cap. Oh, 10 picofarad. Let's say 1 picofarad ka input cap.
Okay.
Okay.
Okay. See, RO depends on GM, right?
Yeah.
GM RO is constant.
Yes, yes.
And likewise, scene is also a function of GM. You can think of it that way.
Yes, yes, yes.
Fair enough?
Yes.
Now the question to you is, boss, how do you decide GM? You figured out these two resistors, Allappa. You figured out these two resistors. And you know that single stage GM is good enough for me. Now the question I ask you is, boss, how do you choose GM? Did you guys understand my question? The only
Yeah,
answer is GM.
that comes on the RO part, right? RO should be sufficiently larger so that GM should be minimum.
No, I didn't get you because
Like RO, so RO we need to get, right? RO also is unknown and GM is
1
unknown.
minute.
So
Let me help you guys. Let me erase this part. So
So
can I replace this op-amp with
okay, model.
GM RO? Fair enough?
Yes.
And scene is connected here.
Correct.
Fair enough?
Yes.
Now can you tell me, only unknown is GM.
Correct.
How do I determine GM?
Yeah, so that comes from the how much is the RO, right? So that is
No, we can do by current.
Once GM is fixed, RO will be fixed because.
correct.
The current. I mean, quiescent current.
No, quiescent current is in your hand.
Yes.
Prashant, the only question is how do quiescent current is all when you implement it in MOSFET, correct?
Correct.
So the question is, how do you determine GM? Because I'm at GM level now. I've not put MOSFETs.
We must be knowing the bandwidth basically.
Perfect. Thank you, sir. You should know the bandwidth. Let's say bandwidth was 100 kilohertz.
Yes.
Right? The system engineer comes and tells you, boss, I only deal with mic signals. The mic signals bandwidth is 100 kilohertz. Can you make the circuit work for 100 kilohertz? The question is, what is the bandwidth of this system?
Okay.
The by the way, Bean is here. How do we determine bandwidth?
Basically, bandwidth is
bandwidth here how
only.
with the output cap, what is the actually where the bus pole
yes,
coming down to connect here.
correct.
The 0.1 nano or 1K, we have it.
Let's okay, yeah. We have 1K and we have
we have
0.1
0.1
per
per
nano
nano,
and we
and we
have
have
this is
this is
VP,
VP,
this is
this is
VN,
VN,
this
this
is
is oh god, I have to read.
I mean, we can get the feedback loop account and see what is the
okay, yeah,
Okay, yeah,
let's
let's
neglect
neglect
scene
scene
also,
also,
okay,
okay,
for
for
now.
now.
filters.
GM
GM
VP
VP
minus
minus
VN.
VN.
Oh,
Oh,
sorry.
sorry.
GM
GM
VP
VP
minus
minus
VN.
VN.
VP is
VP is
VN.
VN.
VN
VN
is
is
feedback.
feedback.
RO.
RO.
Then
Then
you
you
have
have
capacitor
capacitor
and
and
a
a
resistor.
resistor.
Fair
Fair
enough?
enough?
RL,
RL,
CL.
CL.
Fair
Fair
enough?
enough?
Can you
Can
tell
you
me
tell
the
me the
bandwidth of
bandwidth
the
of the
system?
system?
It's a low pass filter only.
Ah,
It is
There is no
there is no
challenge
it is
challenge
about
about
that.
that.
it is actually all the resistance in parallel into C equivalent to R equivalent.
Sir,
I
So
mean,
Okay,
okay,
wait. There are
There are
two
two
options here,
options here,
correct?
correct?
One
sir,
is
1 divided by R plus R naught into CL.
1
1
divided
divided by
by 1
1
plus.
plus.
R
R,
plus
R, R, RL plus R naught into CL.
Yeah,
Yeah,
how
how
can
can
RL
RL
is
is
parallel to
parallel
R
to R
naught,
naught,
na?
na?
everything becomes parallel.
Parallel,
How
parallel.
much parallel resistance comes for the feedback actually that we need to
I mean, transfer function we can do and get.
Wait,
no
one
transformation
minute,
is
one
not
minute,
needed.
one minute.
Yes,
Yes,
Prashant,
Prashant,
that is a
that is a
way.
way.
That is
That
a
is
way.
a way,
Correct?
correct?
You
You
want
want,
you can determine the
determine the
exact
exact
transfer
transfer
function
function
and
and
find out
find out
GM.
GM.
Fair
Fair
enough?
Yeah,
enough?
what is the denominator time constant?
Whatever. It's a
It's a
one
one
pole
pole
system. You
system.
will
You will
determine
determine
that.
that,
Correct?
correct?
Correct.
Yes.
I
I
don't
don't
want
want
to
to
do
do
that
that
entire
entire
math.
math.
Can you
Can
tell
you
me
tell
another
me?
Yeah,
way?
yeah.
Okay. Okay.
Other way, we can convert that CL to maybe uh,
So
impedance.
Sir, can we,
dominant pole
Then
approximately we can take bandwidth by DC gain actually. That should be below.
bandwidth by
No,
no,
I
I
didn't
didn't
get you.
get you.
What?
What?
No, so bandwidth, basically what bandwidth let's say is wants above 100K, right?
100K.
100K.
100K. So
100
basically
kilo.
100K
Kilohertz.
divided by DC gain, that is the first pole location should be just we can
sir, 1 divided by 100K is the gain.
1
1
divided by
divided by
100K is
100K
the
is the
gain.
gain.
What?
What?
Like that unity gain bandwidth will be 1, sir. When we are trying the border plot,
Ah.
that whatever we are getting the bandwidth,
Oh,
Oh,
you're
you are
saying
saying
this.
this.
Okay, that
Okay,
is
that
for
is for
open
open
loop,
loop,
correct?
correct?
yes, sir.
Okay.
Okay.
No,
No,
fair enough.
fair enough.
I
I
accept your
accept your
argument.
argument.
Yes,
Yes,
think
think
of
of
it
it
that
in
way.
that way.
So what
So what
happens?
so,
happens?
so that actually we can see 100K is the UGF. We need to get bandwidth.
No,
No,
one minute,
one minute, one minute, one minute.
Okay.
Okay.
Now
Now
let us
let us
open the
open the
loop.
loop.
Let's not
Let's not
connect any
connect any
feedback.
feedback.
Okay.
Okay.
This
This
into
into
this
this
is
is
your
your
loop gain,
loop gain,
correct?
correct?
V
V
out by
out by
V in
V in
is
is
1 by
1 by
beta, which
beta,
is
which is
fixed
fixed
value,
value,
right?
right?
Because it's a
Because it's a
ratio of
ratio of
resistors.
resistors.
Into
Into
loop
loop
gain of
gain
S
of
by
S
1
by
plus
1
loop
plus
gain
loop
of
gain of
S.
S.
Correct.
Does
Does
everyone
everyone
agree?
agree?
Yes.
So
So
what is
what
the
is the
loop
loop
gain?
gain?
Loop gain.
A naught into
Loop gain
beta.
is
Come
Come
on.
on.
no, loop gain is A beta, right?
A beta, right?
A
A
beta,
beta,
yes. So
yes. So
what is
what
A
is
of
A of
S?
S?
A of
GM
S
into R naught.
Yes, sir.
Yes, sir.
GM
GM
into
into
or not parallel CL. SCL.
Yes.
Yes.
Amazing.
Amazing.
Nice.
Nice.
So
So
GM
GM
into
into
RO
RO
parallel
parallel
RL
RL
parallel
parallel
CL,
CL,
Yes.
CL.
right?
right?
Into
Into
Yes.
this is
this
your
is your
loop
loop
gain.
gain.
Does
Does
everyone
everyone
agree?
agree?
Yes.
Correct?
Correct?
This
Yes.
This
you see
you see
this
this
1
1
plus
plus
loop gain
loop
of
gain
S,
of S,
right?
right?
Hmm.
This
This
bandwidth has
bandwidth
to
has
be
to be
100
100
kilohertz.
kilohertz.
1 plus loop gain.
So
So
can you
can you
guys
guys
tell me
tell me
fast?
fast?
GM into
Odd not.
what is the resistance?
Yeah, odd not parallel RL parallel
GO
1 by
plus GL plus S
SE SCL
SCL.
SCL. Yes.
Right?
Right?
This is
This is
your
your
loop
loop
gain.
gain.
Correct.
Fair
Fair
enough?
enough?
Does
Does
everyone
everyone
agree?
agree?
Into you
Into
will
you will
get this
get this
factor,
factor,
but
but
I'll
I'll
neglect
neglect.
this.
Correct. Barabar. This is
This
loop
is
This is
gain.
10K
10K
and
and
90K,
90K,
right?
right?
Yes, this is log loop. Into that factor will come. Yes, beta will come. No, yes.
You are
You are
seeing it,
seeing
right?
it, right?
Yes.
Into
Into
1 by
1 by
beta.
beta.
One by
I mean,
beta.
into
Yes.
beta.
Beta,
What?
what?
Into
Into
beta
beta.
is loop
Loop
gain.
Into
gain.
beta, that is 1 by 10. Huh.
Fair
Fair
Correct.
enough?
enough?
Yes.
Yes.
So,
So,
GM we
GM we
know.
know.
What is
What is
G
G
naught?
naught?
Is
Is
200 by
200 by
GM.
GM.
Hmm.
What is
What is
GL?
GL?
Yeah,
Yeah,
1
1
milli
by
is
1 by
milli.
1 milli.
1
Huh.
millisecond. Yes.
S
Yes
into
into
what
what
is
is
the
the
capacitance?
capacitance?
1
One
Point
point
one
nano.
nano
1 nano.
1 nano.
into
Into
point
point
Yeah.
1.
1.
1 by 10.
Ah.
Yeah. Point.
Point
Point
1
1
Okay.
GM.
GM.
Okay.
1
1
plus
plus
this
this
is the
is the
denominator,
denominator,
correct?
correct?
Okay.
Right?
Right?
So,
So,
where is
where
the
is the
pole
pole
location
location
now?
now?
Pole location is at 0.1 nano.
Why?
Why?
Solve it,
Solve it,
na.
na.
So,
Okay.
So,
what is
what
the
is the
loop
loop
gain?
gain?
Point
Point
0.1
1
GM
GM
by
by
denominator
denominator
by
by
1
1
plus
plus
point
point
0.1
1
GM
GM
by
by
denominator,
denominator,
correct?
correct?
Hmm.
This
This
expression I'm
expression I'm
writing,
writing,
guys.
guys.
Correct.
So,
So,
it
it
is
is
point
point
0.1
1
GM
GM
by,
by,
or
or
in
in
other
other
words,
words,
this
this
is
is
1
1
by,
by,
no,
no,
let me.
Nishan, this is closed loop. Closed loop gain you're writing, right?
Yes,
yes,
the
the
bandwidth is
bandwidth is
closed
closed
loop,
loop,
correct?
correct?
Yes, but why it is coming 0.1 GM by denominator?
Uh, Beta is
Beta is
point
point
1,
1,
correct?
correct?
Beta is 0.1. That is closed loop gain usually will be A naught by 1 plus A naught beta, right?
Hey,
Hey,
no,
no, no,
yaar,
yaar,
it
it
is
is
1.
1.
Okay, the
Okay, the
closed
closed
loop
loop
gain is
gain is
1 by
1 by
beta
beta
into
into
loop
loop
gain by
gain by
1
1
plus
plus
loop
loop
gain.
gain.
Okay.
No,
No,
okay.
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 Wait,
I
I know
know
what
what
you're
you're
trying.
talking.
You're
You're
saying it
saying
is
it is
A
A
of
of
S
S
by
by
1
1
plus
plus
A
A
of
of
S
S
into
into
beta
beta
Correct.
is
is
your
your
The same.
output
output
by
by
Vin,
Vin,
correct?
correct?
Yes,
Yeah, it
output
is
by
same
Vin.
person.
Or the
I
I
am
am
closed.
writing
writing
beta
beta
by
by
1
Beta
plus
by
loop
1
gain.
by beta. Right. So that becomes loop gain. Yes.
Beta by 1 by
Prashant, you
Prashant, you
see
see
it,
it,
right?
right?
So A's into beta becomes loop gain. Prashant.
Prashant,
Prashant,
okay.
okay.
Do
Do
you
you
agree
agree
V
V
out
out
by
by
Vin is
Vin
A
is
of
A
S
of
by
S
1
by 1
plus A
plus
of
A
S
of S
into
into
beta?
beta?
Yes, I agree on that.
I
I
multiply
multiply
and
and
divide
divide
beta.
beta.
Multiply and divide beta. Okay.
Okay,
Okay,
now
now
I
I
will
will
call
call
this
this
loop
loop
gain.
gain.
Okay.
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 Okay,
Let
let
me.
me.
Why
Why
did I
did I
do
do
this?
this?
1 by
1 by
beta is
beta is
ideal.
ideal.
This is
This is
what I
what I
want.
want.
Yes.
Loop
Loop
gain by
gain by
1
1
plus
plus
loop
loop
gain is
gain is
something I
something I
have.
have.
Hmm.
Correct?
Correct?
This
This
has to
has
be
to be
close to
close to
1.
1.
As
As
Got it.
close to
close to
1 as
1 as
possible.
possible.
Got it. Got it. Understood. Understood.
Right?
Right?
Yeah, yeah, by now I
So,
got it.
I
I
am
am
writing
writing
loop
loop
gain by
gain
1
by 1
plus
plus
loop
loop
gain
gain
as
as
this
this
fellow.
fellow.
Got it.
Close to 1, I did not get, Nishan, what you say.
Sorry,
Sorry,
sorry.
sorry.
Ah,
Ah,
Close to 1, what you say.
because
because
1 by
1 by
beta
beta
is
is
ideal,
ideal,
correct?
correct?
Correct.
If
If
this
this
factor
factor
is
is
close
close
to
to
ideal,
ideal,
if
if
this
this
factor
factor
is
is
close
close
to
to
1,
1,
That is total bracket close to. Correct.
Eh,
Then we will
that
get
is
1 by beta again. That I
then you
then
got.
will
you will
get
get
1 by
1 by
beta.
beta.
Yes. That
The
is
The
okay.
bandwidth
bandwidth
of
of
this
this
has
has
to
to
be
be
100
100
megahertz,
megahertz,
100
100
kilohertz.
kilohertz.
100.
100 kilohertz. Okay.
You're
You're
understanding?
understanding?
Got it.
Got
Got it.
it. So bandwidth of that is 100 kilohertz. What I mean to say is the pole location of that should be then DC gain divided by 100k, right?
DC,
DC gain by.
no,
No,
no.
no, I didn't get you.
No, 100k divided by DC gain. Sorry. See, bandwidth of this meaning the
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 UJS
pole
pole
location
location
of
unit.
this
of
is
this
No.
is
100K.
100K.
Okay. Pole location of 100k is saying. Okay, then sorry. I thought in our case what we take no bandwidth meaning unity gain bandwidth. Unity gain bandwidth is zero frequency, right?
Oh,
Oh,
no, no,
no,
no,
no, no,
no.
no.
That is
That is
where we
where
are
we are
going,
going,
Vikas.
Vikas.
Correct, correct. So if that, then when the pole you are saying 100K, then actually the unity gain comes at loop gain into DC gain into 100K. Okay.
Because the argument should be ulta. You should determine the unity gain bandwidth of the op amp with the keeping in mind the closed loop ka bandwidth. You are understanding, right?
Correct, correct. Okay, okay, correct.
The closed loop, the open, the UGB shouldn't decide the bandwidth, closed loop bandwidth. That is wrong.
Now I got it. What you saying, right? Because this is bandwidth here will actually get us the unity gate bandwidth in the open loop, right?
Yes,
Yes.
sir.
Got it. Got it. Okay.
Did you understand? One should determine the other, not the other way around.
Yeah, the bandwidth in closed loop here should get actually will give us open loop unity gain bandwidth, right?
Exactly, sir.
Got it.
Okay, so where were we? This was we were finding the loop, the pole location of this fellow, correct?
Yeah, 1 plus L loop.
So did someone solve this? Point 0.1 gm by denominator plus 0.1 gm, or you can write it as 1 by denominator plus 1, correct? Denominator by 0.1 gm plus 1, correct? So what was the denominator? 200 by gm plus
1 m
1 milli plus
0.1
0.1 nano s
Yes. Yes.
by 0.1 gm plus 1 is the denominator, right?
yes.
I am solving it haphazardly because I don't have page space. You guys should do it properly, right? So if I solve this, I get, what do I get? Go by gm. Dude, I've made a mistake somewhere. Can you guys spot it? This is 1 by RO. GM by 2. Yar. You didn't tell me only. GO is 1 by RO, correct? Guys, this GO is 1 by RO.
Correct.
This 1 by RO is GM by 200.
Right. So that is missed. Okay. So what is the modifier that is one now? 1 plus
1 plus 1 by 2000 plus 1 milli plus 0.1 nano Siemens into 0.1 gm. Fair enough?
Okay, so we need to find the pole right here. Okay. What is the value?
Wait, yeah. 1 minute. I think I'm screwing you guys. Just 1 second.
You can do there only systematically.
Yeah. Just 1 second. Let us do it systematically, okay?
Yes. The shortcut is not helping here.
Right? So I want this to be some one. I want to find the pole of this location.
Correct.
So this
So let's take only denominator. Okay.
denominator by 0.1 gm plus 1. Fair enough?
1 by denominator. Okay, ठीक है.
What is the denominator? gm by 200
हाँ.
plus 1 milli
हाँ.
plus CL and SCL plus 1. Correct? Fair enough?
Because RO is 200 by GM, right? Okay.
Yes.
ठीक है. तो G naught is GM by 200. Okay.
Does everyone agree?
Yes.
हाँ. HCl plus 1 has come now. Okay, ठीक है. And this one is okay. 0.19 is divided. Okay. ठीक है.
Okay. Now it becomes 1 by 0.5 milli plus GL by 0.1 gm plus SCL by 0.1 GM plus 1. Fair enough?
Point for you divided 200, right?
Hmm.
And then point 1 I can divide it. Okay. Where GM has 1, divided again.
Sorry?
GM has cancelled out. You're saying okay.
Hmm. Does everyone agree?
What is GL you written again? That is 1 milli, right? Again, why you written GL there?
I mean, okay, put 1 milli. Yeah, who cares?
Okay, ठीक है. 1 million, then that value. Yes, okay.
Does everyone agree?
Hmm.
Now, how do we simplify this?
We need to constant term we need to actually combine together, meaning add. But GM, we need to find GM, no?
Yeah, no, I
3.5 something I'm getting
Find
I
3.5.
want
GM
some
meaning
gain by 1 plus S by P. This expression I need.
correct.
You will get this if you do correct. Uh,
Ah,
yeah.
Can take
Oh,
Wolfram Alpha that
no. We'll figure it out. Okay.
I'm getting 3.54 milli Siemens or something.
Just 1 second, guys.
GM and that term. No, actually, see, S by P, we need to do the GM, we need to divide again or multiply something, right? Yes,
Yeah,
whatever.
yeah. Okay, I'm neglecting zero point 0.5 milli when compared to 1. Okay.
Okay.
I can do that, correct?
Yes. Yeah.
So this becomes um, this is some term.
No, GM need to take in the S part also GM is there, no?
Yeah.
We need to either multiply or divide GM with data, but
Okay. So oh yeah. So I can divide it by this term, correct? So divide and multiply. So this becomes take 1 by 1 plus
Plus, yes, that is right.
GM into 1 by 1 plus SL by zero point 0.1 GM into 1 plus 1 milli by zero point 0.1 GM. Correct? Is this correct?
Yes, yeah.
Great. So this becomes
That becomes a
SEL by zero
gain.
point 0.1 GM plus 1 milli. Fair enough?
Yes.
So
Pole is
the pole is zero point 0.1 GM plus
1
1
milli by
milli
C.
by CL into 1 by 2 pi has to be
Frequent. I mean, yeah,
100 kilo.
100.
So
Yes.
what does GM become? CL we know as zero point 0.1 nano.
Yeah, GM becomes 100K into 2 pi point 0.1 nano. Uh, minus 1 milli divided by zero point 0.1.
Fair enough?
Yes. I'm getting 9.3 millisiemens.
GM has 9.3 millisiemens. No?
Yes.
Does everyone get this?
A Vikas.
yes, is getting. I'm getting is this minus.
Yeah, minus only I'm also getting.
Ah.
Mm, oh, yeah. Okay, so where have we made a mistake? Hmm. We have made a mistake somewhere, correct? Circuit. Did I erase the circuit? Mm. Okay, what did we get GM as?
9.3 millisiemens minus.
No, that means to say the direction is just ulta.
Yeah, yeah,
The
direction.
conventions that we took.
Correct.
Fair enough.
Yeah, yeah, I took it
Okay, let's say 10 millisiemens. Okay, for simplicity purpose.
okay.
Now, what is the open loop bandwidth? Okay, so we determine GM, correct?
Yes.
9.3 millisiemens, correct? Now you
Yeah.
have 10K, I mean 1K and CL, right? Can you guys plot the loop gain of S? Where is the UGB? Open loop bandwidth का UGB. At DC it is 200, correct? Approximately at least.
Yes.
Yes, what is the question? Sorry, I missed.
Where is the UGB?
UGB is 100K into DC gain. What is that? 100 DC gain is how much here? Open loop gain.
Oh, no, yaar. I'm talking about the open loop gain.
Okay, open loop gain is how much is open loop gain? DC?
There seems to be some problem, correct?
Open loop gain is 100. How much we assume? 100 or 1000?
No. Yeah, there is a problem, okay? Because the load resistance is 1K, correct?
Okay.
And if you choose some 9.3 millisiemens for the GM of the op amp, the gain will become 9.3 milli into 1K.
That is 9.3 only. That is.
This doesn't satisfy the DC gain specification.
Right. Somewhere I
But
think
it satisfies the bandwidth
mistake.
specification.
Correct. Yeah.
So what is the DC gain? GM into RL, correct?
Correct.
By 1 plus GM into GM into RL. So GM RO RL CL. This is the open loop transfer function A of S, correct?
Okay.
So what is the DC gain? GM
Open loop GM into RO parallel RL.
correct?
Okay.
GM into RO parallel RL parallel 1 by SL.
Yes.
Correct.
Correct. So this has two conditions. The DC gain has to be 100 and the bandwidth has to be, the closed loop bandwidth has to be 100K.
Barabar.
To satisfy both these conditions, you will choose a certain GM, correct?
Correct.
Fair enough. We
Yes.
determine bandwidth के लिए 9.3 millisiemens. But for DC gain of achieving 100, what should you choose? GM as?
GM should be larger, means that
100 millisiemens.
100 how it came because
This is 1K.
This is 1K. Huh?
Yeah, AV is 100.
This is 1K, correct. Barabar.
Do you see it?
Yes.
Yes.
So the GM choice was not actually limited by the bandwidth, but it was limited by the DC gain. And it became 100 millisiemens.
Yes.
Fair enough?
Yes.
Okay.
Now, is this a practical value?
No.
This is just out of this world, correct?
Yes.
Now, can you guys tell me something else that I can do to match the DC gain ka problem?
RL we can increase, right?
Sorry?
RL we can increase, no?
Yes. So
RL is a specification.
No. RL is specific here. So
But
we
we
can
can increase
actually
internally.
internally
Yes. So what should I do?
internally common drain can be used there. Second stage,
So you are suggesting a two-stage op amp.
two stage,
So what did you suggest? You suggested a
common drain in the second stage.
you are saying, boss, I will have a GM here and a common drain here.
Hmm.
Correct? But what happens now? You will run into okay.
Power
Wait.
consumption area.
Oh no. We have a bigger problem. Okay. So you have some GM into uh, GM into some C1, correct? That the common drain amplifier will provide.
Yes. Now the CL will not play any role. CL and
Know the transfer function here of a CD amp.
yes.
And you will have a CL and
So
RL here.
correct.
Correct?
Correct.
Fair enough? The DC gain will be what? Let's say the GM that you've chosen here is some 2 millisiem. No, this is 1K, right? So you have to choose a GM of some 10 millisiemen at least. Correct?
Yes.
So, okay, why did I choose the CD amps GM as 10 millisiemen?
10 milli because the 10 milli into 1K you're saying?
No,
GMR.
the gain of
No,
the
no.
CD
First
amplifiers.
stage we have anyway 10, right? So
Wait, yaar. What is the gain of a CD amp?
CDM gain is 1, no? 1.
one only, right?
Why?
Less than 1.
So what is it?
GM
So GMRO by 1 plus GMRO.
GMRL by 1 plus GMRL, correct? So I want this to give a 0.9 ka gain.
Correct.
And this to give a 200 ka gain.
100,
100.
Overall I get 180.
Okay.
I satisfied.
Okay.
Beautiful solution. Correct? Everything.
No, Nishan, how? 180?
200 is the GMRO here.
Correct. For the first stage.
For the first stage.
Yes.
0.9 is the gain because I've chosen GM as 10 milli.
Okay, point. Okay, got it. Yeah.
Okay. Overall it became 180. Satisfied, no?
Yes.
But what is the hiccup now?
The GM 10 milli, why so much we need to choose? You can go for lower GM, right? For common.
Okay, let's say, what would you choose? 2 millisiemen because?
Whatever is feasible, with low power will make.
Yeah, but because bandwidth is bottleneck, na? CL and 1K.
Exactly.
One weight.
Okay, for CL and
100.
1K, we found GM is equal to 9.4 something. That is equal
Oh,
to 10,
yeah.
10
Correct.
milliseconds, right?
Because
So we have to choose
you
that.
see his point. This bandwidth, what is this? What is the bandwidth of this fellow? What is the gain from this point to this point?
Yeah, gain from this point is point less than 1 only. Yeah.
No. You didn't understand Prashant's point. Okay, let's say this is input, right?
Yes.
This is GM in. What is the transfer function from this point to this point?
This point to
This
this
is
point will
V out.
be into out. Okay.
What is V out by V in?
V out by V in is 100.
Yeah, with this CS test transfer function, that is GMRO and into actually GMRO by 1 plus GMRO plus CD.
1 minute. GM into
The CS test transfer function,
RO
that is
parallel
GMRO
1 by
parallel
SL.
RL 1 by SL.
Which
Right.
is GMRO by 1 plus
GM.
RO S ROCL C1, correct?
C1. Okay.
Agreed.
ठीक है. Okay.
Into what is the transfer function from this point to this point?
That is for GMRO by GMRL divided by GMRL RL into
GM, no. GM 1 by SCL parallel 1K
SCL parallel 1K
okay.
divided by 1 plus GM SCL parallel 1K.
So what does this become?
That usually becomes GM RO by 1 plus S RO C1 only. Na?
this becomes another pole, correct?
I mean, that becomes
GM RL by 1 plus S by P, some pole.
yes.
Fair enough? Where I'll call this as pole of CDM. You guys can solve it, correct?
Correct, correct. Yes,
Whatever
we will.
expression I
Yes,
wrote.
yes, we will check. Yes.
Okay. Now, is this stable? Okay. And then you have a beta, correct?
1 by beta.
Correct.
This is loop gain of S. Sorry. This is into
Point
0.1.
one.
Point 1.
This is loop gain of S.
Correct.
Yes.
Now, 1 plus loop gain of S has to be stable.
Yes.
Do you guys agree?
Yes.
This is a two-pole system.
Correct. When
You will run into what?
Yes, yes.
Multiple
Instability.
stability issues.
We
Stability
need to
problem.
exclude the stability problem. We need to go put the second rule outside.
A Miller compensation or something.
No. Let's not skip steps. Okay. So the motivation is okay. What the takeaway from today's class is very simple. Okay. What are the takeaways? If you try to design
Yeah.
a single stage pipe, I mean a single stage op amp to drive a huge load. Huge load means very low resistance. You will run into problems.
Very huge load. Okay.
Correct.
Okay. What I mean to say is, I did this experiment for a 1K resistance, correct?
Correct.
Can you guys do it for 1 mega ohm resistance and check what is the GM?
Yes, yes. It will be correct.
Okay.
What I
It's
mean to say is,
properly will solid, yeah.
Yeah.
if you take this circuit
Mm-hmm.
and put this as put this as 1 mega.
I mean, bandwidth will reduce, no?
Bandwidth will, I mean, increase, no? 1 by RC is the bandwidth.
Correct. R is increase. Yeah.
What happened?
Correct. I mean, our time constant will increase, basically. The slew will increase.
No, I didn't get you.
No,
It will reduce, man. That say that will less resistance will eat up more, consume more current, right? So it will take a lot of time. Time in the sense it will take this one. And, driving portion will actually.
Prashant, I see his point. Let's say this was 0.9 nanofarad only. Then this pole is less than, I mean, it is some very low frequency.
Very low frequency, right?
This means to say I can't design, correct?
yeah, we cannot design, no?
I cannot design a 100 megahertz bandwidth converter if the load only has very low bandwidth.
Yes.
So let's say this was 10 pico.
10 pico. Oh, 10 pico is huge.
Yeah. Okay, fine. This is design one.
So we need to find the GM.
GM required. Okay.
Yeah.
What is the specifications? The closed loop bandwidth has to be 100 kilohertz and the DC gain has to be 100.
Okay.
Okay.
So you mean the closed loop bandwidth here is nothing but the UGF, right?
No, it's not.
No, closed loop bandwidth. Now, open loop, closed loop bandwidth meaning that is the unity gain frequency, right? For closed loop.
Yes.
Unity gain.
Correct. Yes, so that
Unity gain frequency of the open loop
Open loop.
is the bandwidth of the closed loop.
correct. That's
So, okay.
No. Unity gain frequency. No. You're taking swing ulta, right? Unity gain frequency of the closed loop is bandwidth of the open loop, right? You're saying ulta, right? See.
No, yeah, UGB of open loop.
The UGB of open loop will be huge.
Is the closed loop bandwidth?
No. Closed loop bandwidth will be less. So UGB of open loop, UGB of closed loop is actually the bandwidth of the open loop, right?
Oh, yeah, no, yeah, 1 minute, 1 minute. Okay,
You just
let
check
me
it. Yeah.
explain it to you.
Okay.
Let's say the open loop bandwidth looks like this.
Okay.
This
So what do you
is
mean by
loop gain
bandwidth
of
here?
S.
Now bandwidth meaning you mean to just the 3 dB down frequency or UGF? Bandwidth
This
meaning
is
UGF, right?
UGF.
Right. Okay. This is you calling bandwidth, right?
This is equal to closed loop bandwidth.
Ha. This is equal to closed loop bandwidth. Closed loop UGF, I mean to say.
Ah, because the closed loop, how will it
See,
work?
generally people say bandwidth for the 3 dB down frequency, right? So
3 dB
UGF.
down.
Exactly. They are right,
So
correct.
mhm. So UGF, so bandwidth we mean to say, then actually VGF again bandwidth we getting confused, right? So this open loop UGF
Becomes
closed loop
Closed loop bandwidth.
bandwidth.
exactly.
That closed loop bandwidth is again 3 dB down only, no?
Closed loop bandwidth is 3 down, right?
So
Correct.
correct. That's what I told.
Right, correct.
See,
So this closed loop bandwidth is nothing but the 3 dB down for the closed loop, right? Therefore,
exactly.
correct,
Correct.
true, correct. Got it.
So this is equal to UGF of open loop.
UGF of open loop, correct. Barabar.
You get it right?
Yes.
Mm-hmm.
UGF of open loop
Correct.
is equal to closed loop bandwidth is equal to 100K.
So that means open loop UJF being the pole frequency of open loop itself is the bandwidth.
Yes, sir.
Correct.
No problems, right?
Yes.
No.
Do you guys agree?
Correct.
Yes.
Okay.
CLB is 100 kilo ohms, hertz, right?
Sorry.
Hertz.
Hey, sorry. Yeah, my bad.
And let me take a snapshot.
Okay. Okay. Are you?
Yeah, I took it.
Okay. No.
Recording you have upload, right?
Yeah, I will upload. Now, what is design to? Design to is 100 pico and 1 kilo.
Okay.
Oh, no. This also won't work. Wait, 1 minute. Let me change the specifications. Oh, this won't work. Yeah. Let's say this has to be some 100 femtofarad.
That will pole frequency itself will be nano. Yeah.
Kilo. 1.5 kilo. So this is design 1. This is design 2. Okay. 1 kilo. 100 pico. Yes. Perfect. So this is design 2. Okay. I want you guys to find out GM here and GM here. Okay. Let's call this GM1. Let's call this GM2. Okay. GM2 I tried to find out and I think I made a mistake. I think. While determining closed loop bandwidth.
Correct.
You guys solve it systematically. Okay. I will also solve it systematically.
Okay.
Fair enough?
Yes.
Great. This is important to do because you will realize how difficult it is to drive a low resistance.
Correct.
See, I need a DC gain of 100, right?
Yes.
So this clearly, if I want to implement using a single stage pipe, I need a huge GM because the resistance is 1K. Right? So in one case, the capacitor will dominate. The other case, the resistance will dominate the GM. Okay. Anyway, I'll let you guys come to your own conclusion.
So basically here, so op-amp we need to design it. Basically op-amp we need to design.
Let's assume a single stage op-amp because there are no stability problems.
Yes.
Okay, fine. Can you guys design and simulate?
Okay.
And come to me with simulation results. So the expected output is loop.
Simulation result, you mean to say transient simulation or DC?
No. Do dot AC sim.
AC, AC, AC. Okay, yeah.
Yeah.
I see. So
Okay.
transient, we are not worried here, right?
No. We'll figure out transient later.
Okay, okay.
Okay. At 100 kilohertz, I need 0.707.
100 kilohertz, 0.707 of this
3 dB
open
down.
3 dB down.
7.07 approx.
Uh,
If this is approx 10, this will be 0.707 into 10. Correct?
correct.
Yes.
7, 7, 7.
So this is your expected output.
Right. So AC you want. Okay, yes.
Can you try using to? Okay.
Hey, you guys are welcome to do transient sim also, but this is what I want.
What I know.
Okay.
Okay.
So what you plotted here, AC characteristic versus output, right? Output versus AC
Output characteristic across in frequency.
frequency.
I
Output
think AC simulation is
characteristic.
yes.
Ah,
Frequency versus output only, na, in terms of 20 dB.
Dot AC sim.
not AC only. Yes, we need to apply in the accordingly in the range. Like supply is we can take 1 volt, then we need to apply accordingly
No.
0.5.
Dude, ideal GM use. So
Huh?
there is no supply voltage and all. Ideal GM.
Oh, ideal gem. Oh, okay, okay. No supply and all.
No supply and all.
Supply and we can be anything. Okay.
Yeah.
So,
Got it.
got it. Yes.
LT Spice will have VCCS.
Yes, yes. We can
We have
direct.
cadence, maybe.
Oh yeah, great. If you have cadence, great. You have VCCS.
VCCS, what?
No. For the voltage control current source. For
For the ideal for the
Right, correct. Yes, yes, right. Yeah, right.
Okay.
Multiple pulse, yes.
Okay, guys. Do you want to meet tomorrow?
Yes, yes, we can.
Prashant?
Yeah, I can, but I am not sure whether with results.
Results, yeah, yeah. Tomorrow.
When can you guys give? Wednesday, Thursday, whenever you say.
No, I did not complete the assignment for this week. So
Thursday would be Thursday or Friday we can.
Thursday.
Can you guys mail me? I hope you guys have my mail ID.
Yeah, we can decide now itself so that it will be. Yeah, person, what Thursday or Friday to find, right? Friday
It's
or
fine.
Thursday should be fine for me.
Yeah, Thursday is fine. I mean,
Okay. We'll meet on Thursday. I will also design. You guys also design.
Yes,
We'll
yes,
compare.
yes. We need to spend time. Yes, yes, yes.
Okay.
okay.
Okay, Nisha, thank you.
Okay. Great, guys. Thanks a lot. Great meeting. Probably a little haphazard for my liking too, but I didn't have time to prepare. So don't sue me.
Hey, no issue. We also need to prepare actually. We'll get, yeah. Thank you,
Yeah.
Nisha.
Okay. Great exercise, guys. I hope it was fruitful.
Yes, yes, in fact, indeed. Thank you.
Okay. Thank you, Dhananjay. I hope you understood the class and I hope you do assignments. We'll meet on Thursday anyway with the solution results. Okay?
Thank you.
Okay. Bye, guys.
Bye, bye, bye. Yeah. Good day. Good night.
Haphazard class.